All right, so there's our integral. Let me fix this screen over. By the way, if you ever see this little camera thing here, just let me know so I can click on it so it's not there because I feel like it's a distraction. It doesn't need to be there. So I don't think it's U sub because I don't see a good choice for you really. I mean, technically, there's a thing inside the natural log. You could do a U sub here. You could let U equal 4p. And so I'm just pointing out, if you really wanted to, you could let U equal 4p. Your du would be 4 times dp. And then your p would equal U divided by 4. And you could actually make this harder by rewriting it as U divided by 4 to the 10th power times the natural log of U times du divided by 4. That's not better. It's at best the same. You still have your variable to the 10th power times natural log of your variable. So that's not really getting us anywhere. This is for sure integration by parts because I see the kind of hallmark of have a function multiplied by another function. So I'm going to try integration by parts. And I feel like this is one where people always really, 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 really want to choose the wrong thing for U. It feels so normal to choose U equal to x to the 10th or p to the 10th or whatever your thing is raised to a power. And that's the right choice unless there's a logarithm. So if you're doing integration by parts and you see a logarithm, that should almost always be the thing you're picking equal to U. So here, our U should equal the natural log of 4 times p, and our dv should be the rest, p to the 10th times dp. Our du, the derivative of the natural log of 4p, is 1 over 4p times the derivative of 4p, which is 4. And then we multiply by dp. Those 4s will cancel. That'd be interesting. Yeah. And then finally, your v is the antiderivative of p to the 10th, which is p to the 11th divided by 11. We've got all the pieces. I should also point out, just very broadly, whenever you have your variable to a power multiplied by natural log your variable, it's always going to be a one-shot integration by parts. You're going to let U equal the natural log thing. Your dv is going to be the thing to a power. And then when you rewrite it as uv minus the integral of v du, you don't actually need to write that out. That's going to be U times v, natural log of 4p times p to the 11th over 11, minus the integral of v du, which is going to be p to the 11th over 11 times my du, which does simplify just to 1 over p times dp. And what's always going to happen is your du, your derivative of the natural log, is just going to be one of your variable. And that's always going to cancel out with one of the powers that you already have for the other piece here. So we're going to simplify. We're going to get, I'm going to rewrite this as 1 over 11 times p to the 11th times the natural log of 4p, just because I like writing the natural log last, minus, I'm going to simplify this a tiny bit. It's going to be 1 over 11 out in front. And then p to the 11th divided by p to the first is p to the 10th. We probably could have skipped writing it and just done the anti-differentiation. We're going to get 1 over 11 times p to the 11th times natural log of 4p minus 1 over 11 times p to the 11th over 11 plus c. And then if you wanted to simplify this one step further, you could say it's 1 over 11 p to the 11th natural log of 4p minus p to the 11th over 121 plus c. I should mention there is technically an alternate way of doing this that will probably result in a slightly different by a constant answer. If you really wanted to, you could write this as the integral of p to the 10th times the natural log of 4 plus the natural log of p, which you could then break up into two integrals as p to the 10th times the constant natural log of 4 dp plus the integral of p to the 10th times the natural log of p dp. This one here is just a straight up anti-differentiate it and get p to the 11th over 11 times natural log of 4. This one here, you would do the same sort of integration by parts. I don't think this is the better way to do it. I just wanted to point out that there is a different direction you could have gone. Questions about this? Other questions? I got lots to say, but I'll give you a second. Have to find where does it? Oh, there we go. Yeah. Yeah. There's so many, there's just so many things to do. Let's do that. Okay. Let's do one more kind of interesting thing, and then we'll do something funkier. Well, not funkier. Let's try something like this. I'm going to switch it up and say, do I want to do that instead? Is that going to be worse? That's going to be worse. Yeah, let's not make it worse. Let's try the integral of cosine of the square root of x dx. And I would say this is one of those situations where you don't have a lot of choices. You could do one of two things, in my opinion. I know one of them is right. I don't know if the other one's going to work. One thing you could try is doing a u sub. There's only really one good choice for u. That would be to let u equal the stuff inside the cosine function. So u would be the square root of x, which you might want to write as u equal to x to the 1/2. And then your du is going to be the derivative of that, which is 1/2 x to the negative 1/2, and then we multiply that by dx. Or if you prefer, I like writing it as 1 over 2 root x dx. But I'm kind of sad because I don't have a 1 divided by the square root of x in my integral. So when that's the case, I would say don't abandon ship, but go a different route in that you're going to take this and you're going to solve for x. So I'm going to say that u squared equals x. And then I'm going to differentiate both sides of that. So the derivative of u squared is 2u, and then we slap on a du. The derivative of x is 1, and then we slap on the dx. What I should point out here, just in case you're kind of like, why is the dx du? What I'm really doing here is I'm saying, if I differentiate both sides with respect to u, so if I find d du of u squared and d du of x, on the left side, I just get tu, 2u, sorry. On the right side, I just get the derivative of x. And then I bring the du over to get 2u du equal to dx. That's what's really happening there. And then we can start replacing things and rewrite this as the integral of, well, I follow my own rules. What do I do first? Well, what do I do first? Here's what I'm not going to do first. I'm not going to write cosine of u first, even though that'd be fine. I'm going to make sure that dx transforms into something with du. That is always the first step when you're doing a u substitution. So dx you get replaced by 2 times u times du. So we're going to get 2 times u times du for dx here. And then the cosine of root x is just going to be cosine of u. And now we're in an integration by parts situation. We've got 2 times the integral of u times cosine of u du. And what I have seen over the years, although we're going to do this one this way, but I'll just say kind of generally, what I've seen after lots of time spent with these problems where you first do a u sub and then you do integration by parts, it often means it would have probably worked just to do integration by parts by letting u equal the entire cosine of root x and dv be equaling dx. I don't think that's the better way to do it. I've just noticed that is a way you can do it. I would still do it this way. So then we're going to do integration by parts. Oh, I've already used the letter u. I hate it when I do that. Oh, well. So I'm going to pick w to be the thing that is representing what u usually represents. So we're going to say, or you know what? I'm going to be frank. I don't do that. That's never what I choose to do. What I really do is I go back and like, well, shit, I don't like that. I'm going to change my u's to t's. So I go back and I rewrite them and say, okay, change that into a t, change that into a t, change every u into a t, so I can still use u later. It feels kind of dorky, but you know what? It's better than what I don't like doing, which is using a w. So what I'm really saying here is in this integral, I've chosen t to equal the square root of x. T squared is equal to x. 2t dt is equal to dx. And then I'm going to rewrite my integral of cosine of the square root of x dx as the integral of cosine of t times 2t dt. That is really what I think is better. I know it's more writing, but I don't like using u if I know I have to do an integration by parts later. So then we're going to do integration by parts with this. We're going to let u equal which part? Cosine of t or 2t or just t? Either way, actually. Well, not either way, not all of them. You can either pick t or 2t, right? You can grab the constant multiple if you want to or not. Let's go ahead and grab it just for a change of pace. So my u is going to be 2t. The dv has to be the rest. Cosine of t dt. And then our du is 2 du. Our du is 2 dt. And our v is the antiderivative cosine, which is sine of t. So then putting it all into the usual, oh, I didn't say this before, did I? Did I say the words ultraviolet super voodoo? Okay, so UV minus the integral of V du. One way people like to remember that is UV, like ultraviolet, minus some voodoo. V du kind of sounds like voodoo. So, and then the S for super. So ultraviolet super voodoo is a way people remember the integration by parts formula. It's kind of silly, but it's unforgettable. So we're going to put in some ultraviolet super voodoo here. So we get U times V. So 2t times sine of t minus the integral of voodoo, v times du. I feel like the voodoo one's a little bit more of a stretch, but oh well. Sine of t times 2 dt. And that is something we are able to integrate. We're going to get 2t sine of t. And then before I write a minus sign, I know that the antiderivative of sine is negative cosine. So I'm going to get negative 2 cosine. So that's positive 2 cosine of t plus c. These ones are not my favorite, but they do come up enough, and I think teachers kind of like asking them because it's like they make you use two skills in one problem. You have to do U substitution and integration by parts. So it wouldn't surprise me if something like this were to come up in general. All right, let's talk about some partial fractions. Yeah. So partial fractions is really a method of mostly using algebraic techniques to rewrite an integral so it's something you know how to integrate. That's really like the hard part of partial fractions is actually the algebra, not the integration skills, in my opinion. So let's look at something like, ooh, let's do something like this first. Yeah. We'll do that one second. No, okay, yeah. So let's say we want to do the integral of, sure. Let me think for a second here. Sorry, brain, yeah, 2x plus 3 over x squared plus 6x plus 8. So whether or not you've seen partial fractions, I will say a few things. Partial fractions is a way of rewriting a complicated fraction as a sum or difference of fractions that have less complicated denominators. And the requirements to be able to use partial fractions are threefold. You have to have a rational function. That just means you have a polynomial on the top and a polynomial on the bottom. You have to have the degree on top has to be strictly smaller than the degree on the bottom. They cannot be equal. If the degree on the top is bigger than or equal to the degree on the bottom, the first thing you do is polynomial division, typically. And then thirdly, you have to be able to factor the denominator. So for example, if your denominator is something like x squared plus 3, that doesn't factor. Factor, I'm going to use real loosely here, though, because, yeah, factor is a term filled with lots of regret. I'm going to ask you all a question that has an unsatisfying answer. At least it might, in your opinion. Is x squared minus 3 factorable? The answer is yes. It factors as x minus root 3 times x plus root 3. The better way to phrase this last piece of requirement is that the denominator has to have real zeros. If you set that equation equal to 0, there should be solutions to it. Now, most of the time when someone's giving you a partial fractions problem, they're not giving you something weird that doesn't factor nicely with integers. But just be aware, technically, if you had to integrate 1 over x squared minus 3, you would use partial fractions, and the bottom would factor as x minus root 3 times x plus root 3. But no one's usually going to ask that. So let's see. Do I meet all the conditions? It's rational. Yes. The degree on top is 1. The degree on the bottom is 2. Yes. Does the bottom factor? It sure does. The right factor is x plus 4 times x plus 2. And here's what I'm going to say. Before I do any of that, I should make sure I can't do something easier, like a U substitution. So don't jump to partial fractions. I always call partial fractions a method of later resort. You don't want to do it until you've eliminated easier things to do. So I just want to point out that if you were to make the easier choice and let u equal x squared plus 6x plus 8, your du is exact. Oh, nope. See, I blew it here. I thought I made it look right. See, I was going for it. So this is a good example either way. So I should have tried a u substitution. I meant for that to be a 6 on top. I didn't write a 6. So this is not a good candidate for a u substitution, but you should still check, right? Because if that had been a 2x plus 6 on top, then this would have worked out to be a nice, easy. In fact, I'm gonna turn it to a 6 because I want it to be a nice problem. Sorry about that. I was already like, yeah, I should do it this way, and then I made mistakes. So sometimes you'll have a thing that looks like you could, and actually you totally could do this problem using partial fractions, but you shouldn't because it's much easier to do the u sub here. If we do the u sub, we're just going to get that this integral is equal to 2x plus 6 dx turns into du divided by u, which I would encourage you to get used to seeing, although some people prefer to write it as the integral of 1 over u times du, but either way you slice it, it's the natural log of the absolute value of u plus c, which is then the natural log of the absolute value of x squared plus 6x plus 8 plus c. So I'm going to say it one more time, before you jump to partial fractions conclusions, make sure you have eliminated easier options, typically u substitution. All right, but now let's actually do some partial fractions. So yeah, let's look at a similar-ish problem, but very different. The integral of x plus 1 divided by the same denominator. So now a u sub is not going to be our friend here. We try letting u equal to the denominator. The derivative of that's going to still be 2x plus 6, which is not equal to the top or a multiple of the top. So I will point out, if the top had been x plus 3, which is what I probably meant to write, this would still be a good candidate for u substitution because 2x plus 6 is just twice x plus 3. So just look out for those things. So here's what we're going to do. Yeah, we're going to take our integrand. We're going to factor the denominator as much as possible. And then we're going to set this equal to some simpler fractions, which I know is not very specific. Specifically, what we're going to do is you're going to have fractions where each of your factors shows up as its own denominator. So x plus 2 and x plus 4. There's more to say about that in a bit, but we're not there yet. And then we're trying to solve for whatever constants actually make these two equations equal to each other, or expressions equal to each other. The usual path to solve this is just to multiply both sides by your common denominator. So I'm going to multiply both sides of this equation by the very easy to see common denominator, x plus 2 times x plus 4. The whole point of this step is to get rid of all the denominators. So then you distribute this over there, you get x plus 1. You distribute this here, the x plus 2's cancel, you get a times x plus 4. You distribute it here, the x plus 4 is canceled, you get b times x plus 2. And depending on who your instructor is, they might have shown you how to do this the hard way or the easy way. As you might have guessed, I prefer the easy way. That's usually, or the way that's easier to do anyway. Like sometimes it's not, but I'll show you both ways, but I want to point out, I think the thing I'm about to do first is the thing you should always do first, even if you then have to do other stuff later. Problems like this, where all of your factors are linear, raised to the first power, this will always work completely. For other problems where your factors are linear but raised to a higher power, then you have to implement the second half of this method, which is less good, but still great. I know, right? So here's the easy method. These equations are true no matter what values of x you pick. So pick some convenient values of x, like x equal to -4. If x is -4, then on the left-hand side, I have -4 plus 1 equal to a times -4 plus 4 plus b times -4 plus 2. And -4 plus 4 is 0, and 0 times a is 0. That's why we picked it. So then look at my equation. On the left, I have -3. On the right, I have b times -2. And dividing both sides by -2, I get +3/2 equals b. I want you all to find a by picking a similar convenient value. Not -4, but instead the thing that makes the multiple of b equal to 0. Right. I see some of you mouthing it. That is exactly the number. Negative this many. All right. So we should be picking x equal to -2, because then if you plug that into both sides, on the left side, you get -2 plus 1. On the right side, you get a times -2 plus 4 plus b times -2 plus 2. You really shouldn't write this step. Like, I'm writing way too much work here. You should have just written, I know -2 plus 1 is -1. I know -2 plus 4 is 2, so I get 2a. I know -2 plus 2 is 0, so I'm not even going to write that term. And then I'm going to get a equal to -1/2. I will point out, this is the only time I'll probably do this, that setting a equal to -1/2 and b equal to 3/2 means that when you add these two expressions together, you're going to get this back. That's the whole point of this, is we're showing that this thing here is equal to these two easier to integrate pieces. Let me show you. Normally, you shouldn't do this, right? You don't have to check this, but if you want to check it, -1/2 over x plus 2 plus 3/2 over x plus 4. We're going to multiply those by, or we're going to get, I should say, a common denominator. I'm going to multiply this by x plus 4 over x plus 4, and this by x plus 2 over x plus 2. And let's see, when I multiply it out, I get -1/2 times x, -1/2 times 4, so that's -2, and then plus 3/2 times x, and 3/2 times 2 is 3, all over my common denominator, x plus 4 times x plus 2, and then -1/2 x plus 3/2 x is a whole x, and -2 plus 3 is 1, and oh look, it's exactly the fraction or rational function I started with. So that's what we're doing here. We're just finding the numbers that make this equation true. But then we're going to go back and say, oh, that means that we can rewrite this integral of x plus 1 over x squared plus 6x plus 8 as -1/2 over, sorry, the integral of -1/2 over x plus 2 plus 3/2 over x plus 4. You could take an intermediate step here. I don't think you need to, but if you wanted to, you could write the intermediate step as -1/2 times the integral of 1 over x plus 2 plus 3/2 times the integral of 1 over x plus 4. You don't need to write that out, in my opinion. You can just say, hey, look, I know I have -1/2 times 1 over x plus 2, and the integral of -1/2 times 1 over x plus 2 is -1/2 times the natural log of the absolute value of x plus 2. Same deal here. The integral of 1 over x plus 4 is natural log of the absolute value of x plus 4. And then I have a 3/2 coefficient there, plus c. So the point for most of this is that you're going to get like a something over x plus 2, or something over x minus 3, or something over a linear factor of x, linear function of x, which means that your integral is going to be natural log of that linear function of x. Maybe slightly more complicated, but really not. Questions before we do more examples? All right. Just a reminder, I know you're all very sad. We will not be having class on Friday and Monday. I will not be here. I think I posted on Canvas already, but in case I did, I will make sure there is a posting on Canvas either way. That also means I won't be having office hours Thursday, Friday, or Monday. I won't be here. I think I'll post on Canvas as well. And then I will try to find relevant content that I have recorded before for you to watch. That can be your attendance for the 2 days. So watch the things and then fill out the attendance form, which will be easy to find. Yeah. No. That's for my other class. My other class that's also in this room on this day. So yeah, so that's for my pre-calculus class, not for this class. Grant, unfortunately, is a busy man and is already covering one of my classes on Friday and Monday. So yeah. All right, more examples. So yeah, let's look at. Yeah, I guess that example's fine. I like this example better. So let's look at the integral of 3x minus 8 over x cubed minus 4x squared. So this meets all the criteria. Rational, degree on top is less than the degree on the bottom, and the denominator does factor, and also a u sub wouldn't be good here. If you let u equal the denominator, your du is 3x squared minus 8x, which almost feels like it could work if you just had an extra x on top, but you don't. All right, so be careful here, right? A u substitution is definitely not the right call. It's okay to be off by a constant multiple. It is not okay to be off by a variable multiple here. So even though you can think of this as like x times 3x minus 8 dx, it feels very tempting. It is not the right way to go. It will not work out. So instead, we're going to rewrite our integrand 3x minus 8 over x cubed minus 4x squared as 3x minus 8 over x squared times x minus 4. And I want to point something out here. X squared, this is why I don't like this example, is not a square factor. It's a repeated linear factor. So we're not going to write it this way generally, but you should think of this as the linear factor x minus 0 quantity squared times x minus 4. And here's what happens when you have repeated, meaning to a higher power, linear factors. You get that highest power of that linear factor and every lesser power down to 1. So when I write out my expansion, my partial fraction decomposition, I'm going to write it as a over x squared, the highest power of that repeated linear factor, and then every lesser power down to 1. And then a c over x minus 4. And the reason I need all these lesser powers is because if I don't have them, I might miss something. I will point out that the common denominator of x squared times x minus 4 is still, I should say, the least common multiple is still x squared times x minus 4, right? You could multiply a over x squared by x minus 4 over x minus 4. You can multiply this by x times x minus 4 over x times x minus 4, and you multiply this by x squared over x squared. So this is still a common denominator for all three of those pieces. We need them. And then we do the same thing. I do highly recommend that when you do this, you do think about, oh, I'm just multiplying both sides by that common denominator. So on the left side, we're just going to get 3x minus 8. On the right side, we're going to get a times the x squared to cancel, so you get a times x minus 4. B over x, one of the x's we cancel, so you get b times x to the first times x minus 4. And for c over x minus 4, the x minus 4s will cancel, and you get c times x squared. I said I was going to do the other one the other way, but then I didn't. Oh, well, we'll do it here. So again, I'm going to start picking convenient values of x, things that make some of my terms essentially go away to 0. So one of those convenient values of x is x equal to 4. I plug in 4 for x. Let's see what we get. On the left-hand side, we get 3 times 4 minus 8. On the right-hand side, I'm not going to write out all the things. I'm just going to write out the pertinent things. On the right-hand side, I'm going to get a times 0 plus b times 4 times 0 plus c times 4 squared. That's all I should be writing, because anything times 0 is 0. So then I have 12 minus 8, which is 4. So 4 divided by 16 is equal to c. So 1/4 is equal to c. What is the other value of x that is convenient and is going to make things go away? 0. Here's a hint, by the way, or a tip. It's always the values of x that would have made your denominator undefined, or your denominator equal to 0, or the whole thing undefined. So x equals 4. Oh yeah, 4 minus 4 is 0. X equals 0. Oh yeah, divided by 0. So anything that makes this expression undefined is a good choice for your convenient value of x. So we're going to pick x equal to 0. On the left, we're going to get negative 8. On the right, we're going to get a times negative 4 plus b times 0 plus c times 0. Usually, if you're picking a convenient value, everything except for one term on the right side is going to be 0. So everything is 0 except for one thing. And then a is going to be negative 8 divided by negative 4, which is positive 2. But now, We've run out of convenient values. There's a couple ways to do this at this point. Specifically for this example, or examples where you only have one more constant to find, you can usually just pick any other value of x and try to find it by plugging in the known values you found and then solving for b. That's not the way I like to do it. It requires more arithmetic than I want to do. The fancier way of doing it is by what we call equating coefficients, which you can technically do for the whole process, but it's usually kind of more work than it's really worth. So when I say equating coefficients, what I mean is these two equations, or this, I should say, this equation, not two equations. This equation, the left side and the right side are both polynomials, right? You have positive integer powers of x. For a polynomial to equal another polynomial, each distinct power of x has to have the same coefficient. This is the only way polynomials equal each other. The only way 3x squared plus 5x plus 2 equals some other polynomial is if the other one is also 3x squared plus 5x plus 2. There's no other choice. You have no choices whatsoever. The point being that in this equation, I have x's on the left, I have x's on the right, I have x squareds on the right, I have x squareds on the left, and I have a constant term. So I can equate the coefficients of x squared. I always start with the highest power. It's easiest. And I know that feels kind of silly because you're like, well, what are you talking about, James? How much x squared is on the left side of this equation? It's not a trick question. I mean, it's kind of a trick question, I guess. But if you look at the left side of this equation, how much x squared is over there? None. There is 0 x squared. So I could, if I wanted to, write this, and it wouldn't change anything. But what that means is the coefficient of x squared on the left side is 0. On the right side, we have a little bit more to the story. So if you multiply this out, this term right here would be b times x squared minus 4x. So I definitely have a coefficient of x squared that's a positive b, also a positive c. Oh, look, I know what c is, so that means I can figure out what b is. So b is equal to negative c, but c was equal to 1/4. That's what I mean by equating coefficients. Now, I will say some people like to do this equating coefficients thing more than I do. Some people like to take the whole equation and say, okay, on the left-hand side, I have 0x squared plus 3x minus 8. On the right-hand side, I have a bx squared plus a cx squared. So a b plus c times x squared. And I have an a times x and a negative 4b times x. And I have a negative 4a, and that's my only constant term. The people like to do this, and then say, oh, but then negative 4a has to equal negative 8. Bless you. So that means a is going to be 2. And a minus 4b has to equal 3. But then since I know a is 2, negative 4b equals 3 minus 2. And b ends up being 1 divided by negative 4. And then b plus c equals 0. But b is negative 1/4, so that means c has to be positive 1/4. That is a totally also good way of doing it. I don't think it's an efficient use of my time or your time. I think it's much, much, much faster to do this stuff first. And then if you run out of convenient values of x, then you switch gears and say, well, I'm going to equate coefficients until I get the other things I need. Usually starting with the highest power because the highest power will have less terms to deal with. And then after all this, you're like, thank God. If you're like, no, I haven't finished. I still have to do the integral, right? So once you have done your partial fraction decomposition, then you actually still have to go back and integrate the darn thing. So we're going to go back and we're going to say, great, we are finding the integral of 3x minus 8 over x squared times x minus 4, which is going to be rewritten as our a value, which was, I forgot what it was, negative 2, I think. Positive 2, sorry. Positive 2 over x squared. Our b value was negative 1/4 over x. And our c value is positive 1/4, and that's over x minus 4. And here's how I would think about doing this. anything that's divided by x to the first, or x to the first minus 4, or 2x to the first plus 3, or in general, a linear function of x, leave as is. Any other power of x, don't. Meaning, any other power of x, we write it as something like 2 times x to the negative second, minus 1/4 over x, plus 1/4 over x minus 4. And then we can integrate this and get 2 times x to the negative 1 over negative 1, minus 1/4 times the natural log of the absolute value of x, plus 1/4 times the natural log of the absolute value of x minus 4, plus c. And then I would probably feel compelled to simplify this just a little bit. I would write this as negative 2 over x. I wouldn't actually do anything with this except that if you look up the answer for this in the textbook, it'll probably compactify these natural logs since they have the same coefficient and write this as plus 1/4. And if I factor out a positive 1/4, I'm left with a positive natural log of x minus 4 minus a natural log of x. So I have the natural log of the absolute value of x minus 4 divided by x. Because the positive one minus the other one, you subtract the argument, or you divide the arguments. Plus c. So just be aware, sometimes your answer, which I would probably leave like this, is not going to look exactly like how the book has written it because they've kind of simplified it as much as humanly possible. There is a good reason to do this, by the way. Later on, we start talking about improper integrals, and you have to take the limit as x goes to infinity of this thing. If you write it like this, it's not entirely clear that you have something finite. But here, if x goes to infinity, the limit of x minus 4 over x as x goes to infinity is 1, and the natural log of 1 is 0. So actually simplifying this way is sometimes necessary to see what's happening with the improper integral. All right. Time is it? All right, I got 10 more minutes. There was something else I wanted to see. Ooh, we should do that. For those of you that have talked about partial fractions in your class, did your teacher talk about having an irreducible quadratic factor? Or in other words, integrating something like 1 over x squared plus 1 and getting the arctangent? Okay, good. Because I don't want to do that. So here's what I'll say. If someone says something about that, let me know. Because sometimes it doesn't get covered in the 17B class, and I don't want to teach it to you if you don't have to know it. But if you do have to know it, then let me know and we'll go over it. Yeah. I'm like kind of went, so yeah. So let me skip that and sure. Oh yeah, let's do one like that. Okay, so I got time. Oh, how gross do I want to make this? No, not that gross. Sure. Let's do something like that's terrible, James. Sorry, I'm just trying to make up something that's like, no, fine, we'll do that. X cubed plus 1 over x minus 1. That's a terrible example. Don't write that down. I think there's a factor on the bottom. Well, so I should say it's not a terrible example. It's a terrible example of a partial fractions problem. It's not a partial fractions problem. The denominator doesn't factor. It's also not a partial fractions problem yet because the degree on top is larger than the degree on the bottom. So for a problem like this, what you should do before you try anything else really is polynomial division. Divide your numerator, x cubed plus 1, and fill in the missing terms to make life easier, divided by x minus 1. So what do you multiply by x to get x cubed? You multiply by x squared. You multiply, you get x cubed minus x squared. Subtract x cubed minus x cubed is 0. 0x squared minus negative x squared is positive x squared. Bring down the next term. Wash, rinse, and repeat. When you multiply by x to get x squared, it is x. X times x is x squared. X times negative 1 is negative x. Subtract. X squared minus x squared is 0. 0 minus x is x. Bring down the 1. X times 1 is x. 1 times x minus 1 is x minus 1. Subtract. 0, 1 minus 1. 1 minus 1 is 2. So we can rewrite this integral as our quotient, x squared plus x plus 1, plus our remainder divided by our divisor. And sometimes after you do that step, then the fractional part will then be a partial fractions problem. It's not here. This is a straightaway. Now we integrate. So again, we integrate and we get x cubed over 3 plus x squared over 2 plus x plus 2 natural log of the absolute value of x minus 1 plus c. So if you have a rational function where the degree on top is greater than or equal to the degree on the bottom, polynomial division is usually a good first step. Usually. Occasionally you can get a, man. I hate having to say all the things, but I should say all the things. Here you could have gone a totally different way, but only because the denominator is a linear function of x. If you had wanted to, I would encourage you to try this on your own. I'm not going to do it right now. You could have done a u sub with a back sub. You could have let u equal x minus 1. Your du would have been dx, and then your u plus 1 would have equaled x, and you could have totally rewritten this as the integral of du times a u on the bottom and a u plus 1 cubed plus 1 on the top. And then you would multiply out the top and then divide each term in the top by the denominator and then integrate that and then plug back in when u is equal to. That only works, though, typically in lieu of division if your thing you're dividing by is a linear function of x. This doesn't, like if that had been x squared minus 1 on the bottom, this wouldn't really have worked out that nicely because you can't do this like back sub thing very easily. But yeah, that's a very common other way of going. So I would have felt like I was causing you harm if I didn't say that. Okay, so there was something else I wanted to get to here. Not that one, really. Sorry, this one. I don't like that one either. Garbage. Make one up. All right, so let's look at something more interesting, like the following. 3x squared plus x plus 1 over x cubed minus 8x squared plus 16x. The numbers will not be pretty, almost assuredly. Okay. So I have the usual hallmarks in that rational function, degree on top is less than degree on the bottom, and the denominator definitely does factor. So let's, and oh, wait, I should check. Can I do a u sub? Let's see, if u is the bottom, my du is going to be 3x squared, looking good so far, minus 16x, not looking good so far. So, right, but if this had been a 3x squared minus 16x plus 16 on top, the u sub would have been the way to go. So don't forget about the u sub. It's always lurking in the background. Like, try me, I might work. Okay, but here, not a u sub. So we're going to try the partial fractions path of destruction. And the denominator factors, I can factor out an x. And then I'm left with x squared minus 8x plus 16, which factors as x minus 4 times x minus 4. You definitely should not write it as x minus 4 times x minus 4. You should write it as x minus 4 squared. Everything that's to a higher power, you need to write it that way so that you're reminded to then have that highest power and every lesser power. Oh, I know what I wanted to say. So here we're going to write this as a over x plus b over x minus 4 squared plus c over x minus 4. It doesn't matter which order you write these in, by the way. Like you could have written it in the totally different order. That's totally fine. What I wanted to say over here was just, yeah, sorry. Yeah, no, I'll say that again. Give me a minute. So then we do the usual rigmarole. We multiply both sides by this common denominator, x times x minus 4 squared. I'll remind you, most of the pain in a partial fractions problem is the arithmetic and algebra, right? It's not the integration. That's kind of the easy part. It's dealing with all this. So you have 3x squared plus x plus 1 equal to a times x minus 4 squared plus b times x plus c times x minus 4 to the first. Picking convenient values of x, pick x equal to 0. I get 0 plus 0 plus 1 equal to a times 1 minus 4 squared, which is negative 3 squared, which is 9. So 1/9 is equal to a. I didn't even look at the other ones. I knew they were going to be 0. When picking a convenient value, once one of them is not 0, everything else is 0, guaranteed. The other convenient value of x is x equal to 4. Ish. On the left-hand side, that's going to be 3 times 16, which is 48, plus 4 is 52, plus 1 is 53. On the right-hand side, 0 plus 4 times b. I know the last one's going to be 0. So b is going to be 53/4. What a lovely number. And finally, for C, I've run out of convenient values. So then I'm going to start looking at comparing coefficients or equating coefficients. And it looks like the highest coefficient on either side is x squared. I always start with the highest because, again, there's usually the least amount of terms associated with it. So on the left-hand side, I have 3x squared. On the right-hand side, note the if here, if I were to multiply it out, I'm going to find the coefficients of x squared. No, I'm not actually going to multiply it out. I don't want to do all that work. You don't want to do all that work. You don't need to do all that work. So looking at this would have been x squared minus 8x plus 16. And then a times that would give me an a times x squared and other powers of x I don't care about right now. B times x doesn't have any x squareds. If I multiply this out, this is x squared minus 4x. So I get c times x squared plus other things I don't care about. A is 1/9. So 3 equals 1/9 plus c. So 3 minus 1/9, which is 26/9 is equal to c. And then we can integrate this as the integral of a over x, so 1/9 over x. I'm going to rewrite this as not b over x minus 4 squared, but b times x minus 4 to the negative second, and then plus c over x minus 4. And the way this is going to integrate is going to be 1/9 natural log of the opposite value of x plus 53/4. The integral of this, I'm not going to do the u sub that I would need to do. I'm just going to say u would have been x minus 4. My du would have been dx. And the integral of x minus 4 to the negative second is x minus 4 to the negative 1 divided by negative 1. Plus 26/9 natural log of the opposite value of x minus 4. That is a 4, not a u, plus c. Gross. That's time, but I felt like there was something else I wanted to say. It's not. That's it. That's all I got. Oh, I know what it was. It was if you had something terrible, if they asked you like for the partial fraction decomposition of 2x plus 1 over like x cubed times x plus 1 to the 4th times x plus 3, the partial fraction decomposition would have 8 pieces in it. It would have a over x cubed plus every lesser power of x, so b over x squared, c over x, and then d over x plus 1 to the 4th, and then every lesser power of that, e over x plus 1 cubed, f over x plus 1 squared, g over x plus 1, and then finally an h over x plus 3. That's all I wanted to say was that if you, no one's going to make you do that problem, but someone might ask you, what's the partial fraction decomposition that you would start with for this problem? And then they're just asking you to make sure you know about the whole repeated linear factor thing. All right, now I'm really done talking.